Hello, everyone, and welcome to the final webinar in our Naturalist Notes Webinar Series. My name is Susie Fortner. My pronouns are she and her, and I am the Programs and Operations Director with Friends of the Dunes.
And my name is Daisy Breeze, and I'm the Outreach Manager with Friends of the Dunes, and my pronouns are she, her.
Great, thanks for being here, everybody. We're really excited about tonight's presentation. I'm going to let Daisy kick it off with our land acknowledgement.
Hello, everyone. Yeah, I just wanted to begin by acknowledging that Friends of the Dunes and our staff are working and living on the unceded territory of the Wiyot people, which include the Wiyot tribe, Bear River Rancheria, and Blue Lake Rancheria. Wiyot people continue to be the working stewards of our lands, waterways, air, plants, and animals of their ancestral homelands, which include the stretch of lands between Palut, Kasamuli, Little River, and Ruski, Uwit, Bear River Ridge since time immemorial. Today, we want to honor our placement within the Wiyot territory. Wiyot people and their culture have survived the violent colonization, genocide, and attempted erasure. A large part of a people's culture is their language, and for the Wiyot people, Salutluk is this language. For each webinar, we are introducing a Wiyot word of the day, and today's Salutluk word is Wudulch, meaning dunes. And I apologize for any pronunciations. The Wiyot people were a people of the dunes of Wudulch. So today I am tuning in from Gudini. Oh, I can't do it. Oh my goodness. Okay. Yeah, Gudini, meaning Arcata. And I would like to hear in the chat where everyone else is tuning in from, if using the ancestral lands, if you know them. Please remember to toggle the blue button in your chat box to include both the panelists and the attendees.
You're doing great, Daisy. Sorry, I gave Daisy a thumbs up in there. Excellent pronunciation. There's a lot of interesting sounds in the Wiyot language that aren't normal for English language speakers. So I think you did awesome. Okay, so for those of you that aren't familiar with Friends of the Dunes, we are a nonprofit organization that's dedicated to conserving the natural diversity of coastal environments through community-supported education and stewardship programs. Thank you for joining us for this webinar series and for your contribution. And the funds raised for this webinar series are supporting scholarships for our coastal naturalist training. Oh, I made that slide last minute. It's got a little white bar on the side. Sorry about that. Our coastal naturalist training will be taking place in the fall from September 9th to October 28th. It's going to be an 8-week training this year, a total of 40 hours. And it is a California Naturalist certification program. So upon completion of the program and the requirements, you will be a certified California naturalist. And now, thanks to this webinar series, we have scholarship funds available. So we're really excited to offer up this opportunity to people that might not otherwise be able to afford the program. And I should add that all of these webinars are being recorded and have been recorded. And if you are interested in viewing some of the webinars that already took place, you can still purchase the videos for those webinars. And speaking of the Wiyot language, we had a really great presentation about ethnobotany of the dunes from Adam Cantor, who works as a botanist with the Wiyot tribe. So I encourage you to check that one out.
Yeah, so thank you everyone for joining us on this incredible lineup of webinar series that we have. And this is our very last one, but thankfully we can tune in, as Susie mentioned, and still watch the others that have gone on. So yeah, so just a couple of quick housekeeping items. Please feel free to communicate amongst yourselves in the chat. You can toggle who you're sending the message to by clicking on the blue button in your chat box. If you have questions for the presenter, please type them in the Q&A rather than in the chat box. That way it makes it easier for Susie and I to find those questions at the end of the presentation. You can also control your view of the presentation using the little control button on your right corner. And last, again, these webinars will be recorded. So without further ado, I would like to present our presenter today, Ian Walker. He's a geomorphologist and geography professor at the University of California, Santa Barbara.
Hi, everyone. Thanks for coming. Thanks, Susie, for coordinating this. I think it's a great cause. It's a great way to communicate all the good science and naturalist work that people are doing in this special spot of the coast. Okay,
Yeah,
so
thank you for being here. I'm stopping my share now. Yeah, we're really excited to hear more about all the work that you've been doing.
okay, I'm going to share my screen here. Let's see, make that big. Everybody see this okay? Okay, can you see my cursor okay? I'll probably use my cursor throughout also. Okay, great. Well, thanks again, Susie and Daisy. It's a pleasure to be here. I recognize some of the participants out there, so hi to friends and colleagues. For those of you who don't know me, I am now at the University of California, Santa Barbara, was previously at Arizona State University, and prior to that, University of Victoria in British Columbia, Canada. I've been working on the dunes and beaches here probably back till about 2013 when I first teamed up with Andrea to do some restoration work and erosion monitoring. So what I'd like to do tonight is share with you a bigger picture of the broader research program, but a special project that we have in the region and highlight some of the results from that. To do so, I'm going to paint a broader picture of climate variability and change. And I'm assuming that most of you are familiar with the idea that our climate is changing and that with that comes variability. So storms and erosion events and so on. But I really want to focus in on the Humboldt Coastal Resilience Project, which is a large collaborative project funded by USCC grant and the Ocean Protection Council of California. There are some 12 or 13 partners, including UCSB and ASU and the Fish and Wildlife Service, Friends of the Dunes, and the California Coastal Conservancy. And what I'm going to focus in on primarily tonight are some of our initial results, which you see here. So the big picture is our climate is changing. Most of us have seen enough of this in the news. Well, there can't be enough of this actually, but the reality is our climate is changing rapidly, more rapidly than we've seen in the last million years or so in terms of temperature increases and responses of the global oceans. And the plots that you see here show blue and red trajectories for various things: ocean heat content, ice mass losses, global air surface temperatures, and sea surface temperatures. And these red and blue banded trends represent where we could be in the future. So here we are today in 2021. You can see the past historic trends here, all rising mostly. And then these two trajectories indicate where we could be. So if we focus on sea surface temperature, or this large plot down here, this is sea level rise. You can see that if we take our average condition for 2100, we could be anywhere between 0.43 meters, so about half a meter, and almost a meter in terms of global average sea level rises. We'll talk about this a little bit more, but these two colors represent two different emissions and human behavior scenarios, if you like. If we keep doing what we're doing, we'll follow the red trajectory. This is the burn baby burn situation, where we continue to burn fossil fuels and continue to develop and have population trends that we do today. And the blue is a more conservative approach, where we start to pull things back and think more about mitigating the effects of greenhouse gas emissions. But the point I want to draw your attention to here is that global sea levels are rising rapidly, and we haven't seen these rates of relative sea level change since the retreat of the last ice age, so thousands of years. So let's just look at the recent times here. During the 20th century, according to the Intergovernmental Panel on Climate Change's most recent special report on the oceans and loss of ice sheets and so on, global mean sea level has risen about 15 centimeters. I'm Canadian, so I speak in metric, but 6 inches for those of you who don't speak metric. And most of this we know is coming from ice sheet melting, whether these are alpine glaciers or large continental scale ice sheets like Antarctica. Doesn't matter, we're seeing increased volumetric inputs of water into the ocean because the air masses are warming, melting these ice masses. But there's also a heating effect here. As you heat most substances, they expand. So as the ocean waters are warming, we see sea level rise related to that as well. And we know as well from the same group of hundreds of scientists and others working on this, that the dominant cause of these responses of the atmosphere and ocean is a greenhouse gas emissions response, or the global warming response due to our burning of fossil fuels. So what this means for us who live on coasts is that sea level is rising at rates that are now accelerating more than twice as fast today as they were at the start of the last century. So today we're at about 3.6 millimeters per year. That might not seem like much. It's about 2/3 the thickness of a pencil, but every year superimposed on our tide ranges and storm surges, this means a lot to shorelines and the ecosystems that inhabit those areas. And as you saw in the previous trends, the sea level rise could accelerate, or will continue to accelerate in terms of its rise up to about 1.1 meters as a maximum, or 43 inches by 2100 if we don't change our activities today. Now, that's the long-term trends in terms of sea level rise, but superimposed on this, as I mentioned, are storms and storm surges and wave attack. So you see in the upper right picture here, a picture of Andrea walking down the beach. This is somewhere near Samoa. Very significant scarping in 2017 from some winter storms. So not only will our sea level rise, but the events that cause erosion will increase in terms of where they hit the shoreline, and potentially, depending on where you are in the world, in terms also in terms of their frequency. So storms becoming more frequent and energetic. And we have to recognize too that there are a bunch of other non-greenhouse gas and climatic related impacts. About 30 to 40% of the world's population lives on coastlines or very close to it and depends on these environments. So think of those populations developing and building roadways and airports and coastal resorts and so on and so forth. All of this adding increasing pressure to our shorelines. So many of these coastal areas worldwide, of course, with tens of centimeters of extra sea level, will start to see increasing annual impacts of flooding, erosion, groundwater loss or groundwater salinization, and many other impacts. So in response, it's time to plan. And that's part of what our research is designed to do, is to collect scientific information and make it useful to inform planning for adaptation in the future. Now, I was talking about climate variability. There are two main phenomena, the El Nino Southern Oscillation, or ENSO, and the Pacific Decadal Oscillation, that affect sort of seasonal to interannual climate in our region. Now, if we look at the top plot here, this shows a plot of El Nino, in red. So the El Nino phenomena, as you see in the little globe here, is a tropical Pacific phenomena whereby we have elevated heat and a failure of the countercurrent winds in the tropical region of the Pacific that cause this warm water to move back toward the west coasts of South America and North America. And remember that warm water elevates the sea surface. But with wind changes and extra heat in the ocean, we also see changes in storm patterns. La Nina is sort of the opposite. It's a cool pattern in the tropical Pacific, where we see cooler coastal ocean waters along North America and a different circulation patterns and storm patterns. And this plot over here shows when we are in significant events. And the big ones for El Nino are 82, 83, 97, 98. And 2015, 2016 was a significant event. Currently, we're in a La Nina phase, so cooler average conditions, drier average conditions, which is certainly what we're seeing this season in coastal California, and of course across most of North America with very cool, snow-rich winter seasons. And these La Nina events can be impactful as well in terms of coastal erosion, depending on where you are on the coast. In British Columbia, for example, La Nina years seem to be more impactful for coastal erosion than they do in California, and vice versa for El Nino being more impactful in California. So the El Nino Southern Oscillation has a period of about 3 to 7 years. And you can, kind of plot that out as we go back through time here. We enter one phase or another on roughly that cycle. And they tend to last on the order of 18 months or so. So they're long-lived, persistent patterns in the ocean that affect what happens in the atmosphere and on our coastlines. The Pacific Decadal Oscillation, on the other hand, is a multi-decadal thing. It happens on the order of every 20 years or so, as you can see in the plot here. It is a phenomena that sets up in the northern Pacific. It's defined by what the coastal ocean waters off of Alaska and British Columbia experience and the pressure differences between there and this cool ocean water offshore. So when we're in the positive or warm phase of a PDO, we have warmer coastal ocean waters and very different circulation patterns in the ocean and atmosphere, and vice versa in the cooler phase, so cooler ocean waters, lower sea level elevations, and so on. Now, why am I showing you these two things? Well, they work together or against one another in a sense. So if we're in a positive phase of the Pacific Decadal Oscillation, lots of energy and elevated sea levels in coastal North America here. And then if we have an El Nino superimposed on top of that longer term trend, as we did in 2015, 2016, you can see we're slightly in a positive phase. And if you go back in time, you can synchronize these, meaning that the ocean and the atmospheres have a greater ability to create coastal storms and elevated sea levels. During the El Nino of 97, 98, for example, ocean levels were almost a meter higher than they are on average through a good portion of that season. So that just gives you a sense for how much these effects can have on water levels. So here are some satellite images of what was the King El Nino in 97, 98 compared to the most recent extreme one in 2015, 16. And the blobs that you're seeing here are elevation of the ocean surface. So the white colors here are in millimeters. So greater than 18 or so millimeters of ocean rise due to that ocean water being warmer. And what you see through time in both, but most pronounced in the 2015, 2016 El Nino, is we start to see this bubbling of higher elevation or warmer water propagate up the coast. And it's during that season, for example, the same average storm could happen on that elevated sea level and cause much damage. Never mind if that storm has more energy, it lasts longer, stronger winds, and so on. So we pay attention to these phenomena because they really drive what we're seeing on the coast. In the paper we published in 2015 with some colleagues from the USGS Santa Cruz, and all these other people you see listed here represent some 50 different beach monitoring groups around the Pacific Basin. And what we did is we put our data together here to identify, okay, what happens during an El Nino, because we know it's impactful in North America and it is impactful elsewhere, when we are in a big phase of this phenomena. And this map that you see here shows wave conditions, so significant wave height, average energetic big waves across the Pacific Basin. So you can see along the equator where we have these strong, in the southern hemisphere, we have the strong winds on the boundaries of the Southern Ocean. And then up in the Pacific Northwest, we also have strong storm winds that can drive big wave systems toward the shoreline. The red dots then represent monitoring locations where we've been doing work, and they're representative significant wave heights. So this is a proxy, if you like, of how much energy beaches see in response to waves running up them. And these waves, of course, bring that energy, and if they're superimposed on a big tide or a storm surge, they can cause erosion. And the plot over here then represents how much erosion as a percentage of normal occurs in the winter, which is our most energetic season typically, due to different events. We'll just focus on, this is El Nino here, the MEI, and this is PDO here. And you can see that for El Nino seasons, we see significant erosion of 50 to 90% greater than average along the coast. And for those of you who have been on any coastline in California during an El Nino year, it's not uncommon to see very elevated sea levels and erosion. Now, in contrast, during an El Nino, the western side of the Pacific doesn't tend to see the same trend. If anything, they see below average conditions. So El Nino kind of oscillates. Point being, as climate is changing, we're seeing different responses in the global oceans, but direct linkages for us for El Nino and the Pacific Decadal Oscillation. So for about 3.5 decades now, agencies like the United States Geologic Survey have been conducting what we call vulnerability assessments. Now, vulnerability is a term that means different things to different people. It's kind of sensitive. Nobody likes to be told they're vulnerable. So we've moved toward concepts of resilience, and we can talk about what those mean later. But essentially, what is done is a survey is done from historical air photos, from satellite imagery, tide gauge information, and other accounts and data sets to identify which areas are more exposed to sea level rise. And so a vulnerability assessment does just that. It surveys an area, it looks at trends in things like shoreline position, erosion, the geology and geomorphology of an area to come up with a cumulative index. So I've shown from one of the seminal reports here by the USGS, what their variables of interest are and how they're ranked in terms of low to high vulnerability. So in terms of geomorphology or landscapes and landforms, rocky steep cliffs that are very resistant to erosion are very low, as would make sense. Whereas when you get into barrier systems and beaches and dunes and salt marshes, these can be mobilized very quickly by flood events and high wave energy. And you can see a bunch of other factors. I'll show you some of the results here. And so this is fine and good from a geologic perspective, but there are other aspects of a coastline like human activities, resources, cultural interests, and history that are also important in defining a vulnerability or a resilience and adaptive capacity, if you like, of a certain shoreline. So this is sort of the old school way of looking at it. You can get these maps for free through the USGS, but as you can see, they're very coarse scale. And if you look at the Humboldt area here, you see maybe one little dot of red, but mostly green. And this is not useful for planning. So it's time to sort of turn the dial up and look a little closer at what's happening in your region. So the Humboldt Coastal Resiliency Project is just that. It's a team project that Andrew Pickard from Fish and Wildlife, myself, Susie, and Sue Corbali from the Coastal Conservancy received funding for. And the idea here is to build on work that we'd done back to 2015 on assessing erosion trends and patterns along the Eureka Littoral Cell, which is shown here. So this entire stretch from essentially Centerville Beach up to Trinidad Head is the study area. And the goal of the project is to assess vulnerabilities and exposures to improve resiliency and help develop adaptation strategies against sea level rise and coastal flooding. It focuses solely on the outer portion or most of the barrier systems, and I'll talk a little bit more about that, but the beaches and the dunes that protect the bays and the estuaries and the river mouths and so on. So without that bay and those dunes being the front line of defense, all of these other areas are incredibly exposed. And although there have been vulnerability assessments done on Humboldt Bay and Arcata Bay and the city of Eureka, there hadn't been any work done on the barrier that protects all of these areas. So the objectives, and I'm just going to focus on results from 3 today, are listed here. We'll talk a little bit about the beach and dune geomorphic processes and resilience. We'll talk a little bit about dune restoration as an adaptive strategy for making coastlines more resilient. And we'll talk a little bit about the emerging vulnerability assessment, which incorporates more than just the geology and geomorphology of things, but also the biology, socioeconomics, and cultural interests of the coast. So for some time now, we've been monitoring 73 erosional transects, and thanks to any of the volunteers out there that have helped with this, this is no mean feat to do, often in miserable weather. So we really appreciate your efforts on this. Thanks very much for that. And we'll see some of the results as we go along, but the idea here is to collect information that shows how these systems respond now, how they respond and perhaps recover or not to erosion events. And we've had quite a few of those, particularly the 2015-16 El Nino and the following winter of 2017. Historic shoreline change analysis from historic air photos had been done prior, thanks to Kelsey McDonald for that and GHD consultants. We've done the entire stretch. We'll see a little bit of those results. And those are just sort of the background. So it's one thing to measure, how the beaches are behaving now and what's happened in the air photos, but we need to place them into context with what's causing these changes. And as much as we can in the geologic time frame, which is very long, but also in terms of other activities and infrastructure presence that are ongoing in the area. So I mentioned here a lot of local concern over the Corps of Engineer dredging millions of kilograms per cubic meter of sand per year. Why the concern? Well, this sand, if it's dumped in an offshore site and isn't accessible by waves to move it back to the beaches or currents, it effectively starves the beaches and the dunes. If you starve the beaches and dunes from their sediment supply, they retreat, erode, potentially disappear, and that buffering and flood control capacity and all the other ecosystem services that these beaches and dunes provide is compromised. So we've been looking into other things that help enhance our understanding using LiDAR and satellite information and computer simulation modeling. So let's look at some of those results. So in a broad brushstroke here, the shoreline change work done by Kelsey McDonald and GHD has identified areas of high accretion. So when I say accretion here, I mean that sediment is building up. And what that causes these shorelines to do is prograde or move seaward. And then we have areas that are erosive, meaning they're in a net sediment deficit and the shoreline is retreating landward. And there are some areas that are stable. So, you know, as you go from north to south here, we have some of our highest accretion rates up here between the Little and Mad rivers, stable to accreting in the central stretch in the North Spit, and then as we get to the tip of the North Spit, we become increasingly erosive. The northern portion of the South Spit is generally accreting, and then as we go south over to this right image here, moderate accretion between the bay and the Eel River outlet, and very high, now definitely very high rates of erosion. But you know, historically, the erosion rates down near Centerville Beach were not as high as they are today. And so this causes us to think about why this is happening. Are we losing sediment for some reason? Have we had changes in the river outflux of sediment? Or are there engineering efforts modifying our sediment loads? Or are the bluffs to the south in Mendocino changing? So these are all things we start to think about. We also want to look at other geologic contributions. So for example, the study site, you know, Humboldt Bay is located just north of one of the most complicated tectonic settings in North America, that being the triple junction at Mendocino. So we've got three plates moving, doing all sorts of different things, which causes then upward movements, sideward movements, or downward movements of the plate. So this method called INSAR lets us use satellites orbiting the Earth, different satellites in some cases like this, to track the vertical movements of the crust. So for this study, we used one satellite here that goes back to 2007 and another until 2018. So this is a fairly short window of time geologically. So, you know, this is important for us in that it tells us about vertical motions of the crust and how that might relate to things like erosion rates. But generally, if the vertical land motion, VLM, is positive, the land is coming up, and vice versa, sinking if it's negative. And there are various causes for that. It's not just the Earth's crusts moving around and hitting each other and causing earthquakes, but it can also be settling, as is common around the estuaries and floodplains of river systems. All these sediments over time just gradually settle. It could be groundwater extraction. Water within the pore matrix between sediments creates volume, and when you extract that water, the particles reorganize and the land sinks. Or loading from buildings and other infrastructure, effectively compacting the sediment. So why are we doing this? Well, sea level rise of the oceans is one thing. So this volumetric change we were talking about before is one thing. But if the land is sinking as fast as the ocean is rising, then your relative sea level is effectively twice what the oceans are doing themselves. And in an area that's tectonically complicated, like Humboldt Bay, that's something we definitely needed to look into. And I'll give a big shout out to M. Blackwell here, a PhD student of mine, who published this great paper doing this work for the entire coast of California. So it allowed us to draw on that information to zoom into what's happening in Humboldt Bay. So here are some of the results. Essentially, the hot colors represent land emerging, and the cold colors are land areas sinking. So, you know, the typical or the kind of average condition along the barrier system here is anywhere from -2 to +3 millimeters per year over the observation interval of the satellites. We know that the regional rate of ocean volumetric increase is 4.61 millimeters per year. And this is among the highest rates in California. So we have to consider this vertical land motion as either an offset or in addition to that regional sea level rise. So we add that value or subtract it if it's negative, positive, and we end up with the relative sea level rate. So let's zoom in a little bit here. Lots of groundwater extraction in the area. So the boxes you see here are different wells that M was able to get hold of the record, and some satellite monitoring stations, which are the circles. If the color inside the square of the circle is the same as the surrounding pixels, then that is moving at the same relative rate as the land around it. So for example, if we look into this area of the Eel River estuary and valley, we can see there's lots of subsidence, lots of sinking here. Again, it's a river valley, so these sediments do settle over time. But you can see that some of the well colors are blue here, which means that the water extraction rate in those wells is also very high. But then you can have well extraction, as you see in these other blue squares surrounded by orange or red, where that groundwater extraction doesn't seem to be contributing to the settling of the land due to the removal of water. So let's look in a little more detail here. This is up, Little River's up at the top here. The Mad River pops out about here. Here's the airport. You can see generally this region is rising. So the land is lifting up, and that partly explains why we're seeing, I think, some of the highest beach accretion rates or growth and seaward movement of the shoreline in this area. As we go to the North Spit, so the land fear areas in south are stable to accreting. This is sort of the long-term shoreline trends from the historic air photos. And you can see that most of that area is rising also on the order of about 1 millimeter or so a year. But as we go to the tip of the North Spit, we see increasingly erosive conditions. Now, the jetty itself interrupts currents, interrupts sediment transport, and interrupts wave patterns as they move along from south to north. So part of this starvation and erosion we see here is pretty typical around obstructions like jetties or breakwaters, meaning that you've interrupted the littoral or coastal current that would be delivering sediment to the other side. So that's part of the signal there. Then we go down to just between Humboldt Bay and Eel River. You can see that we've got roughly stable shorelines here with some areas that are sinking, and the shoreline response is to be generally accreting. And then as we go down towards Centerville Beach, we get very high rates of erosion here, and you can see much of that stretch is sinking. So that could explain part of the signal there. And as we go, here's Centerville Beach here, Ferndale and so on, you can see this area is emerging. I'm not sure that that's labeled right, but I can check into that. So the point is that some areas are rising and some areas are falling for a variety of different reasons, but in some areas this helps us explain why our shoreline erosion rates might be the way they are. In other words, if the shoreline is sinking, you would expect to see more rapid rates of erosion if you didn't have the supply to make up for that sinking beach. Next thing I want to share with you is our Floridian restoration efforts. There are several sites, I'm only showing 2 here, along the Eureka Littoral Cell where various types of restoration of the Floridian are underway. And I say various types, meaning for some people this means an ecosystem or species specific strategy of creating new habitat. And for others, it means trying to restore an ecosystem that functions biogeomorphically, meaning that the plants and sediment transport patterns that are normal are held in place. So if we look to the left here, you can see the stretch along the Landfear dunes. This central portion that looks a little more connected to the beach is a restoration site. And you can see the sites to the south and north of that have very steep erosive bluffs. These are vegetated with Ammophila arenaria, which is a non-native invasive species. And you can see the morphology of that is very different than the dunes that have been restored. And we'll talk a little bit more about that. The one on the right here was an overwash where the foredune was breached in the Eel River Estuary Preserve, just south of the Eel River outlet. And you can see the overwash fan here. And the response here was not really a dynamic approach in trying to restore the ecosystem in terms of its plant cover and geomorphology, but one of just filling the hole, so to speak, and with some introductions of plants to try and stabilize that again. The idea here is that foredunes, these buffers of sediment that protect the landward areas from erosion and from flooding, are in harmony with their ecosystem, or well, they're part of the ecosystem. They're in harmony with their plant communities. So the plants determine the form of the dune and its ability to function and recover. So here we see a stretch of the landfear dunes that was eroded in January of 2017. This is about 1.5 meters in height, so lots of sediment lost. Later that year in May, we see some sand ramp rebuilding, so wind gets blown up against the base and reconnects the beach. As we see later on in that season, we've got much more connection between the beach and the dune, meaning that that sand that's delivered to the beach by waves can then be blown into the dune and beyond the dune to keep that dune in a positive sediment budget state. As soon as we shift into a negative sediment budget, we're in erosion mode and the dune may not recover, depending on how much supply comes in. But the other point in this picture is that these dunes naturally can respond fairly quickly depending on their vegetation cover and the frequency of erosion events. So the hypothesis here is that dunes that are stabilized by, say, an invasive species, this dark green line here, over time might not be resilient to or have a recovery to increasing storms and sea level rise if they don't maintain that landward sand transport and the ability to migrate. Keep that buffer rolling, if you like, as sea level rises and storms increase. Whereas areas that are dynamically restored, the idea is that you can keep that foredune shape and its vegetation communities, and it will migrate upward and landward as sea level rises. That migration is important if you want to keep the barrier as a buffer. If the dune can't migrate and maintain its sediment volume, it disappears and you end up with flooding and encroachment of the sea. So what we've been doing at Landfear is monitoring the site using terrestrial laser scanning. And we have several different treatment plots here. So we've got a control site here, which is sort of the native Dune Mat plant community. We have an Ammophila site, so this is the invasive site where no vegetation was pulled. And then we have Elmus mollis, Dune Mat, and then a combination of Dune Mat and Elmus mollis communities that have been restored, so planted and reintroduced. And over time, you can see different responses in the landscape here as the system eventually comes back into balance with its new plant cover. So in this initial stage, you can see lots of landward sand movement. This is nothing to be alarmed about. This is actually a good thing. We've increased the storage volume of that dune, which means we've increased its buffering and capacity and its flood control. But over time, as the vegetation is reestablished, we slow that down, we start to build a slightly taller dune, and then we end up with a dune that's in balance again. So several growing seasons later, now we have very nicely functioning dunes, as you saw in that earlier aerial picture of the site. So what this plot shows you here is just a cross section of how that Ammophila, that invaded, that unnatural dune, if you like, behaves. It's got a very peaked shape, a very narrow landward extent. Yes, it's tall, but you can see over time that changes as well. But the point is, if this continues to function like this over decades, you're not seeing any landward movement or increase in volumetric storage, or if you like, buffering capacity of this type of foredune. So you're seeing the profiles we've been measuring cycling through time here. Now let me show you the other two treatment types. This is the Dune Mat, which is the native alliance, and then Elmus mollis, which is a native dune grass in the area. And what you'll see in each of these, first, the beach erodes significantly, that's normal, but that's the supply to the foredune. But if you watch over time, you see gray lines moving upward and beyond the crest of the foredune. And that's critical because that increased volume and supply of sediment provides the buffering capacity. It also provides the disturbance and the nutrients required for many of these plant species that are responsible for keeping this dune in place and resilient. I know this is a pretty psychedelic map. Just bear with me here. So the blues and reds represent erosion or deposition. Blue being deposition and red being erosion. And what it represents is, from our mapping, change over time. So you're looking at, in the central picture here, how much sediment has eroded or been deposited and where, the red line being the crest of the foredune, this pale green line being the toe of the foredune where it meets the beach. Over our most recent monitoring intervals. So Zach Hilgendorf, big shout out to Zach here. He's been working hard on this. PhD student at ASU. He's got our data from like last week here already, which is fantastic. But if you look at the behavior of the system since we started measuring in November 2015, so some 6 years or so, the beach has remained in a net erosive state. And again, these beach systems will do that for several years, and then they'll go into a phase where they start to accrete sediment. The concern is, with sea level rise, if it happens faster than the beaches can adjust, or if sediment supply declines over long periods of time, the beach system erodes and you can't supply the foredune and you start to lose the foredune. So we're not concerned yet about the beach being erosive. This could be part of the natural cycle. But what's most encouraging is that the restored plots, so we've got our Dune Mat, Elmus mollis mix up top here, Dune Mat and Elmus mollis individual plots, and then we get into our invasive species and then the natural control sites that weren't modified. The blue areas here are a good thing. This increased volume and height and width of the foredune is what we're looking for. So these are doing fantastic, and as predicted. When you get into the Ammophila foredune, you can see there's lots of red pixels up here. So erosion of the dune in many areas. There has been some delivery to the top of the dune, but you can see that it's much further seaward and will be scarped out yet again during the next big storm event. We've seen this over and over. Whereas the native dune that wasn't modified also sees a fair amount of sediment deposition on the seaward face and closer to the crest. All to say that native and restored sites are outperforming by far and away the erosive, or sorry, the non-native Ammophila foredunes. And it's this type of dune that dominates pretty much the entire stretch of the Eureka Littoral Cell. So our interest through this demonstration project is to see, first, does it work? It appears to here. And second, could we use it elsewhere to try and build more resilient dunes that store a greater volume of sediment and have a greater buffering capacity? Now, the final thing I want to show you here is the vulnerability assessment that's underway. So just a map to orient you, and the stretch of the Eureka Littoral Cell is in purple here. That's the study area. And then these areas 1 through 13 here represent different study reaches. So these 13 reaches were chosen based on their geomorphology and shoreline change rates. We're focusing again only on the beach and dune barrier system. And where we have large dunes migrating landward across the barrier, we include that as well. All the way down to Centerville from Trinidad Head. So we have 3 levels of assessment. Just to show you how deep we're going here, and a big shout out to Laura Shinsato, a master's student of mine at ASU, who's done a lot of work on this with Zach Hilgendorf. What we're trying to get to for the end of the project is what we call a comprehensive or all-encompassing vulnerability assessment. And that is made up of all of these 21 or 22 different variables that we've collected data for or measured ourselves. And then we add them up and we categorize them to come up with both socioeconomic as well as environmental factors that contribute to vulnerability. And I think that's important to distinguish. Most of the early vulnerability assessments would have focused primarily on physical. We've included biological, and we've included natural hazards. All of these things combined, even though some of them are unrelated to climate variability and change, affect the ability of an area or a community in that area to respond and adjust and adapt to climate change. And then we've got the socioeconomic factors. So the Wiyot tribe was generous enough to work with us to provide some of their important archaeological sites. Population density numbers are important, land use activities and categorization, and then critical infrastructure from emergency response to pipelines, power lines, roads, and airports. And then we take the data for these, and they come in different formats. We can talk about that later. And we coarsen them into a 1 through 5 or 1 through 10 scale. We run it through an equation to give every pixel that is about 100 meters by 100 meters, to give every pixel a value. And then we stack all of these different variables on top of one another. We group them, and we come up with a comprehensive vulnerability score. So here's what the maps look like for geomorphology. So depending on the type of landform, we have the one being not as vulnerable. So upland areas where we're not encroached by waves or sea level rise are not as vulnerable given their elevation compared to beaches and salt marshes. So that's a pretty straightforward one. Coastal slope. And these, you can see these are kind of banded. We're really only interested in what the beach sees. So what that means here is this stretch near Samoa, for example, all receives this value of 4 right across the barrier because the fronting portion of that part of the barrier has a certain slope value. So areas of lower slope are more susceptible to wave overtopping, sea level rise, and storm surges. That's the idea here. And then the relative sea level change. So this combines both the regional sea level trend as well as that vertical land motion that we talked about earlier. And so, you know, pick your areas of interest, and you can see these pixels tell you that in terms of relative sea level rise, some areas are experiencing more than others. Emergency response infrastructure, power line presence, and the pipeline presence is similar. We have a map for that as well. So where it's present or absent, in that case, we give it a 0 or a 5. So obviously the power lines and the pipelines are pretty critical infrastructure specific to those areas, even though they serve broader areas. So we've considered all these sort of infrastructure related factors. Cultural sites, although we don't identify the sites, we link their presence to a shoreline in terms of the number of sites that could be impacted if that stretch of shoreline were to disappear or flood. Population densities, same thing. And then land use type. And we can go into the details of these later if you like, but all to say that we took in a broad range of geographic factors here to come up with the assessment. And then we start to lump them up. So in terms of physical vulnerability, and recall that's all of these factors here, we start to see at these reach scales, some areas pop out more than others. Similarly for cultural vulnerability, depending on the number of archaeological sites, population density, and land use, we see a ranking emerge as well. And these are coarsened up to 1 to 10 scales. And for infrastructure, all of these things combined, you know, is there a fire hall present? Is it an evacuation route? Is there a pipeline or power line there? Those are all factored in. So you can start to see as you put these together, certain areas start to emerge as more vulnerable than others. And then we've got this sort of next level, the environmentally sensitive areas or vulnerable areas, and then the socioeconomic. And some of them align and some of them don't. So for example, up here in the Little River area, we see fairly low economic vulnerability, but fairly high environmental vulnerabilities. So you'd have to peel back the layers to figure out what that is. And we can talk about that, of course. And there will be a report forthcoming that shares these maps and the results and interpretation from that. So in summary, we're looking at coastlines that are changing rapidly. Beach dune systems and barriers, as we call them in geomorphology, serve dozens of important roles in ecosystem services. Flood control is one of those. And erosion protection. So in terms of the ability of this barrier to protect Humboldt Bay and the communities behind, we need to be thinking about resilience. And so we've taken stock of how the system's behaving now and then the various things that are causing change, knowing that these systems will continue to change. So this idea of sediment movement is not something to be concerned about. It's just how and where and can we maintain the barrier to maintain its protective role. So we know that the shoreline is eroding in spots and other areas are prograding. We know that some of the areas along the shoreline are going up and others are going down. And sometimes there's a correlation between those two things. And we know that the restoration projects show much promise for promoting a more resilient beach dune barrier system. And as we pull all of this together to compile our vulnerability assessment, we're getting a pretty good idea on where we need to be targeting efforts for developing these adaptation strategies and how that might best be done depending on, you know, what your cultural interests are, what the land use activities are, infrastructure presence, and so on. So with that, I'll just put this up. There's so many people to thank for this. This is not just me. I use the royal we lots because there's so many people that have been fantastic. And I'm very, very thankful to be working with so many great people. And I think with that, I'll just turn it over for some questions.
Great, thank you, Ian. That's so much wonderful information. Yeah, and as you mentioned, there's a lot of people working on this project, the Humboldt Coastal Resilience Project, and there's also a lot of components to this project. So this is really just a snippet of it. And I encourage folks who just want to learn more about it. Zach Hilgendorf, who was mentioned and some of his images were shown, he did a great short talk for our Dunes Co-op public meeting, which is posted for free on YouTube on Friends of the Dunes YouTube channel. So you can go check that out and hear some from Zach and what he's been working on. Great. And so if you have some questions for Ian, please go ahead and type them in the Q&A. And Daisy and I will read those off. It doesn't look like we have any just yet, but I did see one pop up in the chat. Yeah. So let's see. Patrick Sullivan asked, did you consider the risk to or loss of agricultural production?
The short answer is no, but we do consider agricultural activities through the land use component of the vulnerability assessment. Of course, as you know, there are many areas that are on the barrier itself that are pasture or cropland and other agricultural activities, even transportation to agricultural sites. So it's in there. It's just when it comes to production, it's kind of like property values and other fiscal things. They change a lot. They're very sensitive. Whereas you can use a proxy like the presence or absence of agricultural activities of different types and assign value to that is, not in dollars and cents, but it's a value of relative vulnerability. And so that's how we've rolled it into the assessment so far.
Yeah, thank you. Next question by Summer. How would you quantify whether groundwater extraction is causing land subsidence?
Yeah, so what we've done so far is look at the well records, and there are only 3 with long records, but I think we've got a hold of 22 different well records, and then we compare that to the surrounding vertical land motion map. So if an area is sinking due to groundwater extraction, then all the wells and all the pixels around them for vertical land motion will show the same thing. High groundwater extraction, so a loss of head or level in your well as the land is sinking, because you're basically taking away the capacity for the aquifer to recharge itself. So I think I put a question mark beside that, or I didn't make an attribution to that in terms of what's going on around Ferndale and the Eel River Valley. But some of the wells correspond to ground subsidence, but they don't all. And the longer term well records don't show a clear association with ground subsidence. So that's the long answer. If we had more wells and they were longer in record, then we could make a better attribution. But there are some spots where it seems like there's a correlation. But if your well record's only 5 years or 10 years long, then you got to be careful in that, because you could see that could be a variety of different things causing that.
Thank you. Okay, so we have another question from Mike Cipra, who is also the executive director of Friends of the Dunes. He said, Dr. Walker, great presentation. How best do you think we can share this information about the value of habitat restoration in creating coastal resilience?
Hi, Mike. Great question. There is a component, as Susie knows, of, well, and you do too, I guess, of the HCRP that involves outreach and education. And I think that's really kind of a gold moment there to take some of this information in a way that's more digestible maybe than some of the maps and plots that I show, but turn it into, and we've done this in other projects, turn it into educational signage, have school groups and other groups that would visit Friends of the Dunes, for example, listen to a scientist or a restoration specialist talk about it. So those are some ways. I think too that, you know, so I've seen sites from state parks near Table Bluff and other restoration sites along the coast that are fantastic. And at the Dunes workshop, it was a year ago or a year and a half ago, you know, a whole bunch of managers and science nerds got together to just walk around and visit some of these sites. And that's an important way to share that information amongst practitioners and scientists, right? So, I mean, there's lots of ways to do it, and that's something we'll explore in the HCRP is like, how do we get this information out there so it's useful to people?
A lot of outreach is needed.
Yeah.
Yeah, next question by June James. Did you take the land movement related to the faults in Humboldt Bay area?
Thanks, June. Yeah, good question. So that all shows up in the vertical land motion maps. It doesn't really matter why the land is moving up or down, and there are a bunch of causes, as I mentioned. So like, you know, just sediment settling in a river valley to tectonic movements and plate faults. So that's in there, that's in the mix. When it comes to sea level rise, it doesn't really matter why the land is rising or sinking, it's just by how much. And then you add that to your local or relative, sorry, your regional sea level rate to get your impact on the shoreline. But yeah, that's all picked up by the satellites. And so people who study, you know, plate movements and earthquakes look at that type of information all the time.
Okay, I've got another question here about restoration from Peg of how much work is it to do the restoration? It sounds very labor intensive.
Well, there are people in the audience that are much more experienced at actually doing the restoration. I feel like I just swan in and take pictures and measure things and then I go away. But I have seen the restoration in action at Landfear, for example, and I'm involved in another site at Oceano Dunes. It's incredibly labor intensive, depending on how you do it, but manual pulling it's hard work. Using machines is not as hard, but it's a little more tricky sometimes, or you know, in sensitive habitats that might not be allowed. So there are a variety of different ways to do restoration and different phases of the restoration. But in the case of Landfear, for example, removing that invasive grass is very labor intensive if it's done by hand, for sure.
One more restoration question. What restoration methods have you considered for along the Bay and 101 corridor to protect infrastructure and address SLR?
Sea level rise. Yeah, thanks, Summer. That's a good question. Every time I drive along that stretch of 101 behind the bay, I think, wow, the days are numbered here. You know, at high tide, the water is at highway level. It is, and this isn't a cop-out, but it's beyond the scope of our project because the city of Eureka and Arcata have done their own vulnerability assessments, and I don't know to what extent they are recommending or involved in restoration activities. On the 101 side of the bay, there aren't big dune barrier systems, right, that could really be restored and functional. You know, you have some dikes, you have some revetments and other engineering things that have been built, but there's not a, you know, the wetlands would be more of a concern in restoring those because you know, they can move with sea level rise also, but they're squeezed right up against the highway in some spots. So the focus of what we've been working on is that first line of defense, if you like, from the ocean, and that's the outer barrier and the beach and dune systems there.
Great. Yeah, I just wanted to add to the restoration of the dunes, for one, that as we mentioned last week, I don't know if we mentioned this week, but Friends of the Dunes has resumed our restoration work days. So if folks are interested and are local, you can come out and do some restoration on your own and remove some of that Ammophila and find out how labor intensive it is. It's really fun, actually. I mean, we go out there and on our properties, we do only hand removal of the Ammophila. At some other sites locally, they do use heavy equipment, such as up at Little River State Beach. They've used heavy equipment in the past. Out at Landfear, it's primarily hand removal, and then sometimes with the assistance of certain herbicides to help keep the Ammophila at bay. But yeah, lots of work to do that dune restoration, but you can definitely come and find out for yourself. And for the bay restoration, for folks that are still on the call, if you haven't been out there, I encourage you to go visit Freshwater Farms Reserve that's managed by the North Coast Regional Land Trust, because it's a really, really great example of what wetland restoration can look like. And they've removed several tide gates and restored the wetlands there. And they're also still grazing cattle on the property. So it's a great place to see both the agriculture and the restoration taking place. And there's some great information out there about different wetland restoration and the armoring of the bay and how that can help with sea level rise or not with the armoring. So great information out there about that stuff too. I think that's all the questions we had, unless people have any more to type in there. We are really looking forward to having some published results for this project and continuing our outreach efforts. Friends of the Dunes is handling the outreach component for the Humboldt Coastal Resilience Project, and we're really excited to get this great information out in the world. So yeah, thank you, Ian. Thank you for being here and sharing all this great information with us.
My pleasure. Yeah, it was great. I mean, it's not the same as being there in person, of course, but hey, we're in this weird time, but yeah, it's good to share this stuff. I should say too that if anybody wants to learn more about the project, feel free to reach out to Susie or myself, and we're happy to answer your questions. Or there will be more public workshops and dissemination events as we go along. COVID hit us all a little bit and set us back in some ways, but we're coming very close on the vulnerability assessment, and we'd like to get some more information and kind of local knowledge on that. So feel free to reach out.
Great, thank you. Yeah, and once again, this is being recorded. So if you missed some of the information, there was a lot of math in your presentation actually. So I might have to go back and like absorb all that once again. But it'll be posted in the next couple of days, so you can rewatch if you're interested in getting that information again. All right, well, thanks everybody. I guess that wraps up our whole webinar series. So thank you for being here, and thank you, Ian, for sharing all that great information with us. And we hope to see you out in the dunes soon.
Great, thank you.
Thank you.
Thanks. Good.